Okay, so as you know, we've been dealing with complex numbers and dealing with imaginary numbers, and the last lesson was mostly review of how to deal with those and how to combine some of those terms. So you've probably done all of that lesson in one way or another, but today should be new material, and what we're going to do is deal with those complex numbers again and look at them graphically, and then put them into or deal with some trig with these complex numbers too. So graphing actually sounds a lot easier than it, or is a lot easier than it sounds. In general, like the complex plane, like we have a new axes for our imaginary numbers and our real numbers, but it basically goes along with like how we normally graph with x and y. So we're going to call the x-axis to represent the set of all the real numbers. And then our y-axis is going to represent the set of all the imaginary numbers. And again, like this is not the x and y coordinate grid that we know, like the x and y Cartesian plane. This is the complex plane, so we are dealing with something that's like slightly different, but in general we plot them kind of the same way. So instead, you know, this is our complex number. Our A always represents our real numbers, and the BI represents our imaginary component. So if we're going to say that A is all of the x-axis numbers, then we have some x value, and then our y-axis is representing the imaginary numbers. We're going to have some B component that's telling us how far in the imaginary plane or the y-axis that we're going to go. So essentially B just turns to y. So we have x plus yi. The only difference here is that when we deal with our complex numbers, they're not just plotted as points. They are a combination here, like x plus yi, so it's not just a point like x comma y, it's a vector. So that just means that when we plot our point, we're going to draw our vector from the y-axis, or from the origin to that point. So this is like our a plus our bi, so this is our x plus our yi. So we have 2 on our x-axis and then 3 on our y-axis. So we're out here in space. This is 2 plus 3i. And again, it's not that single point. It's a vector because it's not like x comma y. So we draw it from the origin. So that would be our complex number plotted on the complex plane. So same idea here. -5 on the x-axis. And 1 on the y-axis, 1i. So we have a plotted point out here in space. It's a vector, so we're going to connect it. And this would be then the complex number -5 plus I. These two look a little bit trickier because we're dealing with not just, like we don't have an x value here, we don't have a y value here, we're just dealing with one number, but we're going to treat it the same way. This is like 0 plus 2i. So we're 0 on the x-axis, 2 on the y-axis. That would be our plotted point. This is our vector plotted from the origin. So 0 plus 2i is going to be this complex number. So straight up. And then this one, -3 on the x-axis, but we don't have any imaginary component, so it would be 0i. So we're at -3 on the x-axis, but we're not going up and down in the y direction at all. So this is our plotted point and our vector coming from the origin. So this would be -3 plus 0i. So since we're dealing with all these vectors, it should look kind of familiar to you. Like we're dealing with like drawing arrows on the not Cartesian plane, but on a plane. And with that arrow that we're drawing, we're creating some direction and we're creating some magnitude. And magnitude is really the length, how far that vector goes. And so now what we're going to do is we're going to see how this angle, this direction, we can represent with, you know, some degree measurement, and that means that we can use trig. Like we can kind of create this little triangle. You can kind of see this one forming here. That's a 90-degree angle. We could represent that theta value, and then we can talk about that vector not in only terms of x plus yi in that way, but with some sort of direction and some magnitude. And so that's what polar form really does, and polar form can be really helpful in a lot of ways, but you'll just have to trust me on that. it comes up a lot in calculus, and it comes up a lot in physics. Dealing with this polar form is treating it with some sort of direction and some magnitude. So this way, again, I've been saying this, polar form is a way to represent this complex number, but only instead not using x plus yi, but using the direction. So that means using some angle, some theta value, and then the length, how far that vector actually goes, and we call that thing magnitude. Magnitude is basically the hypotenuse of a right triangle. It's you calculate magnitude with basically like the distance formula. So we're going to do it like more like the Pythagorean theorem, but it's basically like the radius that we're going out, or the hypotenuse of our triangle. We've done that a lot anyway. So what we're going to do is we're going to take our rectangular form and we are going to put it into the polar form, but we're going to do this in a sort of a derivation way, and it's actually not that hard because we've done things that are so similar to it. So let's say that we have some complex number plotted out here, and this would be x plus yi. So that means that we have some x component, which is a real number component, and we have some y component, which is that imaginary component, and this would be some x component that we're going out. This is some y component that we're going up or down, and then this angle that's formed we're going to call theta. That's our direction. And then this would be our magnitude. I'm going to call that r. We've drawn this picture a lot. We actually drew this picture in chapter 2 maybe, when we were talking about like trig. Maybe it was chapter 1, I guess. We were talking about trig for kind of the first time, and we drew a picture like this, and we talked about how this hypotenuse was not always 1 because that would only be on the unit circle. So in the rest of what we're doing today for the complex plane, this r value is not going to be 1. So like if we were going to represent this in sort of a trig manner, like here I am standing at that angle, I can talk about cosine of that angle as a ratio of my adjacent side over my hypotenuse. And usually we just say cosine of theta equals x, but that's when our magnitude is 1. But in all of these cases, our x component is not going to be some fractional thing like we just saw in these ones. Obviously, like 2 and 3 makes this magnitude not 1, so we can't just represent it as cosine of x equals or cosine theta equals x. And likewise, we can't just say that sine of theta equals y, but we can represent it as a ratio of our opposite side over our hypotenuse. So the main reason that we're doing this is because we want to take our rectangular form of x plus yi and put it only in terms of our magnitude, which is r, and our angle, which is theta. So all that means really is we're going to take this equation and we're going to solve for x. So I would multiply by r on both sides. So I'd have r cosine theta equals x. Should have left a little bit more space. But that's one of the substitutions that we're going to make. And same thing here. I multiply by r on both sides, and I get r sine theta equals y. And we're going to plug that back in and substitute it back into our rectangular form. So instead of x, we have r cosine theta. And instead of y, we're going to write r sine theta. So then this is the same complex number, but only represent it with our magnitude that we have and the direction that we're going. Now this can be written a lot of different ways. One thing that we can do, since both these things contain an r, is factor it out. And a lot of times when we factor that out, we write the I first. There's no really good reason. Except so like this really is our trigonometric form, our polar form. Cosine theta plus I sine theta. But a lot of times like this gets really annoying to write because we're dealing with cosine of theta and sine theta of the same angle. Like those theta values are identical. And so because this kind of gets cumbersome, a lot of times it's written like r, instead of writing cosine plus I sine, we write it as cosine plus I sine theta. So write it as like r cis theta, but it means the same thing. It's really a combination of cosine plus I sine. It's just a notational difference where we can actually combine those in that same way. But no, if you do see that, that's what it means. It just means the same thing. And you can write it either way. I don't really care. So this r value, remember, is our magnitude. It's our length. It's really the distance that's from the origin. So it's really like we're going to use it as the hypotenuse of our right triangle. And since it's a hypotenuse, since it's a length, it's always going to be positive. And this theta value is our normal theta value that we are creating like with the x-axis. But remember, we can be in any quadrant, so we could have a theta value of like 100 degrees, which would be in quadrant 2. And so that means like our cosine value, our x value would be negative. So we can represent our direction that way. So because we're going to be like having all these different theta values in different places, and we have x and y coordinates, and we're going to be converting from polar coordinates to rectangular coordinates, or rectangular form to polar form, a drawing will usually help you figure that stuff out. So there's really a couple things that you need to remember. You need to remember what polar form looks like. Like that's something that you need to memorize. And if I were you, I would memorize these things. Not that they're really that hard, because we know that cosine theta usually equals x, and the only difference is that we have this r value, which this is our original. So you can just kind of remember this picture and then derive it every time. But if you remember r cosine theta equals x and r sine theta equals y, that will help you out immensely too when you're converting from rectangular form to polar form and vice versa. Okay? Okay, so we are going to do that on the back here. We're going to convert, and I am going to write out what our x is equal to, which is r cosine theta, and our y is equal to r sine theta. And our polar form, which is, I'm going to write it as, well, I'll write it both ways. And which these mean the same thing. That just like helps us, again, identify what we're trying to get to, which our end product goal is. Like this is all polar stuff and our conversion from that. Okay, so we're going to draw a picture. First thing that we're going to do is draw a picture so we can figure out what type of magnitude that we're dealing with, what type of direction we're dealing with, and if we plot our vector on our complex plane, that allows us to do that. So we're at negative x and or negative root 3 in the x direction and positive 1 in the y direction, and I don't really care what that looks like. I just know it's over here in quadrant 2. And this would be negative root 3, and this would be positive 1, and here's then the triangle that's created. So our r value is really easy to find because it's just the hypotenuse of our right triangle. So we would do that by using the Pythagorean theorem. So we get 1 in 3, and then the square root, so we'll get that our r value is 2. So that's really easy. Like we're converting it, we're trying to make it look like this. So the only thing that we need now is our direction, which is our theta value that would go in there. Oops, I guess I'll write it this way. 2, we just solved for r. So we just need to figure out our direction, which again is our theta value. So we know we're dealing with something that's between a 90 degrees and 180 degrees. We're just going to, again, we're going to use degrees for this whole thing. We don't have to use our radian measurements. And this is why you did that little special right triangle review, is because we are dealing with a lot of special right triangles here, and we don't really see this happening. Well, we're really used to seeing like root 3 over 2 and 1/2 and root 2 over 2 and root 3 and all that other stuff, but we're not used to seeing special right triangles arranged this way where our hypotenuse is not 1. But if you can recognize that this still is a special right triangle, then you can figure out the reference angle really easily, and you don't have to do extra work. So I know, like looking at my hypotenuse, this is 2, and then that means that this opposite side that I have is half of that, which means that this angle here is a 30-degree angle. Another way you can think about that is if I divide everything by my hypotenuse and make my hypotenuse 1. So this 2 divided by 2 is going to be 1. I'd have 1/2 and then root 3 over 2, which is that 30, 60, 90 triangle, and across from 1/2 is a 30 degree. So this is going to be our theta value, the thing that would be going into quadrant 2, what I'm going to represent here. So if I'm calculating that, this 30 degree reference angle in quadrant 2 means that my theta value is 150 degrees. So that's my answer for our polar form. Okay. Again, process, draw a picture, come up with R. If you have it in rectangular form, you could just use the Pythagorean theorem, and then you can come up with your theta value reference angle by looking at either special right triangles, or sometimes you have to do it like in a trig way, and you have to calculate it. But for now, we're just going to, that's kind of our general process to get to that point. Like all three of these are dealing with some special right triangle, or something that you could just easily calculate rather than using your calculator to find it. So again, let's come up with the drawing. This is our x value at -7, our y value at -7. So we're down here in space. This would be our rectangular coordinate. Come up with my right triangle, -7 and then -7. This is isosceles right triangle, meaning that this angle here is going to be a 45 degree angle. And our hypotenuse, you could use the Pythagorean theorem for this, but you don't really have to. This one, since it's an isosceles triangle and it's a 45, 45, 90 triangle, that's a special right triangle. So our hypotenuse, our R value, really should be 7 root 2. Now again, this is something like you could use the Pythagorean theorem for, but if you know your special right triangles, then this saves you some time. So that's our R value. Our theta value is in quadrant 3 with a 45 degrees, so it's 180 plus 45, which is 225. So all around 7 root 2 cis 225. Or again, you could write it as 7 root 2 cosine of 225 plus I sine 225. That means the same thing, or you could distribute that R value throughout. Either way, that's the same representation of this rectangular form of our complex number. Okay, last one where we're converting to polar form from our rectangular form. This one we don't have an x component, so it's 0 plus 3i. So we're on our y-axis. We're going to go down 3 units, so that would be our plotted point. Here we go. This is a little bit weird because we don't really have like a magnitude. We don't really have like I shouldn't say that. We do have a magnitude, but we don't have like a triangle like we've been dealing with where we have to solve for the Pythagorean theorem to come up with our R value. But our magnitude, remember, is like really just the distance from the origin, and we are going down 3 units. So our magnitude when we only have one component is really just 3. And it's going to be positive 3, remember, because our magnitude is always positive. So you might be tempted to write -3 here because you know that this y component we have is -3, but R is always positive. So our R value is 3. Our angle is on the y-axis. Down here, that's going to be at 270 degrees. So our answer is 3 cis 270. And I want you to make a little note here that it's not -3 cis 270. That R value is not negative. So just be careful, because that's like one of the biggest errors that I see, is that if we're dealing with something with an x component that's negative or a y component that's negative, and that's the only thing that we see, we're really tempted to make that R value negative, even though in these ones none of them were, even though like x and y were both negative in these cases, like this case, and x was negative over here. Our R value is always positive. Our magnitude is always a positive number. Okay, we're going to go backwards now. We're going to go to rectangular form, which is the x plus yi. So that's our end goal, is to get to that point. We're going to do the same process. We're going to draw a picture. So our R value here is 5, and our theta value here is 45 degrees. So that allows us to compile what our picture looks like. So we have some vector, some point. We have some x component, we have some y component, but we don't know either of those. We just know that our R value, which is our hypotenuse, is 5, and we know that our angle here is 45 degrees. And that will allow us to solve for our x and our y component. Knowing that it's a 45-degree angle means that we have an isosceles triangle, and you just did a bunch of practice on special right triangles where you can actually solve for and go backwards in the same way. You could use the Pythagorean theorem and just replace this with x and come up with that value, but instead, when you're dealing with a 45, 45, 90 triangle and you're given the hypotenuse, if this is x, this is x root 2, if I'm going backwards, I have to divide by root 2. So that's what we're going to do. We're going to solve for x by dividing 5 by root 2. And we rationalize. And we get 5 root 2 over 2. That's our x value and our y value, since they are the same in my isosceles 45, 45, 90 degree triangle. So my x component is 5 root 2 over 2. My y component is 5 root 2 over 2. And then I have my imaginary, just I tacked on the end. So that would be our polar form. The other way you could do this is you can kind of think about it like, okay, well, I know that the cosine of 45 degrees is root 2 over 2. And if I distribute that 5 to it, I get 5 root 2 over 2. And same thing over here. Like if I distribute that throughout and like change it back to and actually calculate what the sine of 45 degrees is, I get root 2 over 2. And then I can look at it that way too. That's another way to check rather than going through that process. But either way, like both of them are really good ways to go about it. Or like this is a good way to check, or this is a good way to check to make sure that you calculated things correctly. And this is in quadrant 1, so both of them are positive, so that's another good way to check, or good thing to look at. Okay, same thing, 600 degrees is our angle, this is our R value. 600 degrees is hard to plot because it's something that's over 360 degrees, so I'm going to find a coterminal angle. So I'm going to subtract 360 degrees, and you get 240. So that's sitting here in quadrant 3, 240 degrees. Our R value, a distance from the origin, the length of that vector is 8. This would be 180 minus 2, or 240 minus 180 is a 60-degree reference angle. So it's a 30, 60, 90 triangle, which you know information about. The side opposite to the 30-degree angle, sorry, is 1/2 of our hypotenuse. So usually it's 1/2 3 root 2 or root 3 over 2 and 1. So this side here was going to be 4, but it's going to be negative since I'm in quadrant 3. And then the side opposite my 60-degree. So this is x root 3, and then 2x. The side opposite my 60-degree is going to be root 3 times my small leg, which is going to be negative 4 root 3. 4 root 3, but then again, like it's in quadrant 3. So this is my x value, so negative 4. This is my y value, minus 4 root 3, and then I. And so sometimes you see it like this, or like that. All these things are equivalent. They all mean the same thing. So as long as you kind of have, I would space, if you're going to use the first one, just space out that I a little bit so you know that it's not underneath the root. But all those forms are equivalent. You can put that I in any place. Okay, last two, we're going to convert to the other form, which just means if we're dealing with polar form, we're going to convert to rectangular form, and if we were dealing with rectangular form, we're going to convert to polar form. These are ones that aren't going to be special right triangles, so we're going to have to use our calculator, so get that out. We're going to draw a picture for both these things. So our, just to kind of help us out for a little bit, this is our R value, and this is our theta value. So I know that in this theta value of 115 degrees, I'm going to be here in quadrant 2. So this whole thing is 115, and my R value here is 6. So I can come up with, there's a couple ways to do this problem. I can come up with this angle by subtracting from 180, and you get 65 degrees. And then you can come up with your x and your y component by writing a ratio of side lengths. Like if I'm here at this angle, I can come up with my y value by doing sine of 65 degrees equals y over 6. And my cosine value coming up with the x would be, or coming up with the x, I would use cosine. Cosine x equals 65 over 6. But no, remember that this thing is going to be negative here. So whatever answer you get, so whatever decimal, it's going to be negative. So let's write down both those ratios. Standing at that angle, let's deal with cosine first. So cosine of 65 is equal to x over 6. And then we could solve for x by multiplying by 6 on both sides. And we type that into our calculator, and we get 2.54 approximately. And know again, for our rectangular form, that x value, I'm going to write that down here, something I, is going to be negative because I'm in quadrant 3. And then we could do the same thing for our y component, like standing at that angle. I would be using sine of 65 degrees is equal to y over 6. And again, I would solve for y by multiplying by 6 on both sides. We type that thing into our calculator. We get a decimal approximation of about 5.74. So that's one way to do it, is to draw your picture, come up with your reference angle, and then make sure that your signs are appropriate. The other way is to know that really our rectangular coordinates are x equals r cosine theta and y equals r sine theta, and not draw a picture, although a picture always helps. And I know that my r value is 6, and I know that my theta value here is 115, and that should give you a negative 2.54 rather than your positive 2.54 that you found here. That's because we used the reference angle. This time you're using the whole angle, so that will also work. And same thing here, like you could plug in the sine of 115, and you should get the positive 5.74. So that's another way to do it and get the same answers, and this is a little bit less work. Like, we're essentially doing the same thing because this is really r cosine, but this is not the theta value that we originally had. It's the reference angle for the quadrant that we were in. If this was in quadrant 1, then we would be dealing with all positive values, so the reference angle and the theta value from the original problem would be the same. But when we deal with different quadrants and we come up with that reference angle, that changes the sign. It doesn't change the actual value that we're going to calculate, but it changes whether it's positive or negative. So you have to make sure that your x and y values are reflected in the quadrant that you're in. So that's just one, like, if you're going to do it this way, which sometimes is because you don't have to memorize anything, that's fine. Just know that, like, you have to go double check and make sure that this thing has to be negative because you're in quadrant 2. Like, that's important, is to make sure that your value here at the end recognizes or reflects what quadrant you actually are in for this complex number. Okay, last one, a little bit easier. We're going to convert to our polar form. So again, what we're ending up with is some r cis theta, or some r cosine theta plus I sine theta. They represent the same thing. So we're given our x and our y values. We need to come up with r, and we need to come up with our direction. So let's draw a picture. We're at 5 on our x-axis, -4 on our y. So here's our angle, or our vectors. So this value here is 5, this value here is -4. So we can easily, again, come up with r by using our Pythagorean theorem. So we'd have 5 squared plus -4 squared equals r squared. So 25 and 16 is 41. So our r value is going to be the square root of 41. Nice thing about our polar forms is we never have to rationalize. Like, I shouldn't say never, but when we come up with our r, a lot of times now we'd be thinking like, oh, when we come up with the cosine, we're going to have to use like 5 over root 41, and then we're going to have to rationalize with this radical. I always get annoyed, like, when I come up with a radical and the hypotenuse, I'm like, oh, I'm going to have to rationalize. But for polar forms, we don't have to rationalize, so that's kind of nice. And then the last thing we need is a direction. So we're looking at this reference angle, or that's the easiest way. Like we can come up with this angle because we know a ratio of two side lengths. So I can represent this with some sort of trig function if I'm dealing with my opposite side and my adjacent side. Or now that I have my root 41, I could deal with any of them. But tangent's usually the way to go because we are already given like our opposite and our adjacent from our problem. So you could solve for your theta value first rather than solving for your r first. So this would be negative 4 over 5. And I'm solving for the angle, I'm solving for the direction. So we know how to do that. We just need to take the inverse. And if we type that into our calculator, we get negative 38.66. That gives us our reference angle. So we just want to make this in quadrant 4, so I'm going to add 360 degrees or do 360 minus this 38.66. Either way is fine, and you'll get 321.34 degrees. So I have my r, I have my theta, so I can just plug it into this one or this one, doesn't really matter. So we get root 41, and I'll use the cis, and that's 321.34 degrees. There we go. That's our polar form. So it's a lot of like pictures really help, and it's a lot of like the kind of the easier trig stuff that you already know. You just have to remember what polar form looks like, and you have to remember what rectangular form looks like as big picture ideas.